Today I will present the work Disentangling Visual and Written Concepts in CLIP with Antonio Torralba and David Bao. We've noticed that image classifiers can be confused when text appears in an image. For example, these two images show the same cup, but the CLIP predicts the other one to be mom. We also noticed that when we generate an image to match a descriptive word, instead of synthesizing the object, we often synthesize the word itself. For example, the image shows both peace and the letter peace. These results lead us to the question we study in this paper. Can we separate a network's representation of visual concepts from its representation of text in images? Specifically, we are interested in disentangling the representation of the CLIP network, which learns a joint embedding for both images and text. We wanted to know if CLIP represents the picture of the dog the same way it represents the picture of the text dog. Normally, CLIP measures similarity between image and text using a separate image encoder and text encoder. But to test the processing of text that appears in images, we rendered the word on an image and used the image encoder for both. Surprisingly, we found that the encoding of text in an image is similar enough to the encoding of the visual image that it can perform an image classification task far better than random. In other words, the image encoder thinks these two images resemble each other. If a network sees a picture of the word the same as the picture of the object, then it might not have a representation of words that don't have objects. We test that by retrieving a text image using a text embedding. But instead of looking just at English words, we're interested to see how well the network can retrieve random strings from images. While the network can read English words very well, it can read random nonsense strings almost as well. This suggests it might be possible to separate the text concepts from the visual concepts. Here's how our method works. We learn independently two orthogonal projections, one to learn to spell, to encapsulate the knowledge of the network has about text, and another one, forget to spell, to ignore the text in images and focus only on the visual part. We trained the projection matrix using a dataset of 5 CLIP embedding tuples: an image, a class label string, a text string, a synthetic image with the text rendered on it, and a natural image with the text rendered on it. We pulled the representation that correspond to the text meaning closer and the ones that carry the visual meaning apart, or vice versa. We do it by learning on orthogonal projections of the embedding vectors using contrastive learning. To see if our method is able to separate representations of text in images from visual concepts, we study generated images. Using the VQ-GAN-CLIP framework, we generate 2,000 images conditioned on single words using CLIP loss as an objective, and respectively the two learned projections. Images generated using the original CLIP model have both the visual representation of the word, but sporadically also text in the image. The images generated using the forget to spell model don't show the text, but rather focus on the visual aspect of the query. And the learn to spell images tend to contain the text. We quantify the appearance of the text with an OCR detector. The learn to spell projection images show much more text than the CLIP model, and on the flip side, the images generated using the forget to spell model show close to zero detections. Additionally, we highlight the importance of the orthogonality of the projection. Intuitively, it retains the knowledge of CLIP. Our experiments support this idea. We see that the images generated using the unregularized forget to spell model collapse to a single pattern and color. Conversely, the OCR detections in images using the unregularized learn to spell model are significantly lower than the ones in images generated with the orthogonal projection. We also wanted to know if our method mitigates the typographic attack. To this end, we collected a data set of 180 images of 20 objects and 8 typographic attacks. The confusion between the typographic attack labels in the CLIP model is greatly reduced in the forget to spell model. Lastly, we test the out-of-domain generalization capabilities of the learn to spell projection and showed that despite greatly reduced dimensionality, the learn to spell projection achieves close to the same accuracy as the CLIP model, despite being only trained on synthetic text images. Thank you for your attention.